Hi everyone. If you recall in Chapter 19, we learned about Gibbs free energy and how that relates to the spontaneity of a reaction or a chemical process. In this video, we're going to learn how Gibbs free energy relates to redox reactions and how to tell whether a redox reaction is going to be spontaneous and related to delta G. So let's take a look. After this video, you should be able to explain the relationships between the cell potential, delta G, and the equilibrium constant for that reaction. And also, you should be able to use delta G to calculate the cell potential and vice versa. So let's get started. So what does free energy have to do with redox? Well, if you recall, reactions are spontaneous if they have a positive cell potential, or as we learned in the last video, EMF, electromotive force. So as long as the E cell is positive, it's going to be spontaneous in the forward direction. Well, this equation should look very familiar to you. To find the E naught of a cell, we need to know the standard reduction potentials of our reduction half reaction and our oxidation half reaction. So we just subtract one from the other. And just want to point out, this is true for all redox reactions. It's not only true for voltaic cells. So we don't have to just have this process occurring in a voltaic cell. Any redox reaction, the overall cell potential is going to be equal to this equation above. Now, if you recall, Gibbs free energy is what tells us whether a process is spontaneous or not. So negative delta G means it's spontaneous under those conditions. Positive delta G means non-spontaneous. And of course, a delta G equal to 0 means that the system is at equilibrium. So this is a very important point here. When the cell potential is positive, which we know is spontaneous, then the delta G will be negative, which we know is spontaneous. So positive cell potential means negative delta G. Negative delta G means positive cell potential. So let's put these in an equation form. And this is a very, very important equation. Delta G equals negative N F E. So we already know what delta G is. That's the Gibbs free energy change. N is the number of electrons. So do you remember when you balanced redox reactions, the last thing you did to each of the half reactions before you put them together into an overall reaction was make sure that the number of electrons that were being transferred were equal to one another. That is the number that goes right there in that N. So whatever that magic number was, the least common multiple between the two half reactions, that's the number that goes there. If you're already looking at a balanced redox reaction, you'll need to know how many electrons total were being transferred. E is just the cell potential. And then we have this new variable, F, and it's actually a constant. It's called Faraday's constant. And it's 96,485 coulombs per mole. Now recall that a coulomb is a unit of charge. So coulomb is a charge. And if you recall, 1 coulomb equals 1 joule over 1 volt, because we actually learned, I think in the last video, that 1 volt equals 1 joule over 1 coulomb. So this is going to be a very important unit to use sometimes with this number. So in some cases, we won't use coulombs per mole. We'll use joules over volt moles. So remember the order of operations. We multiply before we divide. So I can tell that both the volts and the moles are in the denominator of that unit. So the Faraday constant will be provided to you on the exam, but make sure that you know how to use it. Let's give it a shot. So first I'm going to derive a new equation for you. So let's just start with the equation that we just got. And I can use these little knots to mean I'm talking about standard conditions. Let's rearrange this a bit. So let's solve for E naught by itself. So I'm going to go ahead and get I'll leave the negative down there for now. Do you recall any equation that from chapter 19 that delta G is equal to? There were quite a few of them. There's delta H minus T delta S. But the one that relates to equilibrium was delta G equals negative RT ln K. So the delta G equals negative RT ln K, of course, temperature being in Kelvin. So let's actually substitute this in for delta G. So we're going to get our E naught for the cell equals negative RT ln K over negative NF. So I can clean this up a little bit, get rid of the negatives. So E naught equals RT over NF times ln K. So I'd like you to pause. All right, so how is everything related to each other? So we've talked about redox reactions, we've talked a lot about Gibbs free energy and equilibrium. So there's a reason that this chapter comes last in almost every chemistry textbook, because we're going to need to know all those concepts from 3 different chapters to put it all together and understand electrochemistry. So we just said that we have this important equation, delta G equals negative NFE. And then we also said we've got this older equation, delta G equals negative RT ln K. So here's a nice little visual for people who would like to see the relationship a little bit better. So let's take a look. Here's delta G, which we did in the last chapter. And we knew that we could relate delta G to K by this equation, delta G equals negative RT ln K. So if you know delta G, you can figure out K. If you know K, you can figure out delta G. Don't forget, K is always referring to equilibrium. So we don't want to use Q there because K is always referring to the equilibrium position of the reactants and products. How can we convert between K and delta E? This is that equation which I just derived, and I asked you why it was important. If I know the equilibrium constant for a particular process, then I'm able to calculate the cell voltage, and that's really important if you're trying to figure out which battery should I use that's going to provide such and such voltage. This would be a really important equation to use. And finally, if you're trying to figure out whether something's spontaneous or not, maybe you know the cell potential, but you want to know the delta G of the reaction, or vice versa, you can use this equation here. So these are very, very important equations to understand, and so you can figure out which equation to use in each situation. So let's try one. For this reaction, we know the delta G is positive 87 kilojoules per mole. Now I'm telling you that the standard reduction potential for nickel 2+ is negative 0.28 volts. And I'd like to know, what value do you calculate for the standard reduction potential of the half reaction shown below? So this is our balanced redox reaction. At the top, I'm going to give you a hint. This is overall, and it wants to know the value for the half reaction shown below. So go ahead and pause, get out a sheet of paper, and give it your best shot. All right, and let's take a look. The correct answer was D, negative 0.13 volts. If that was a little bit too fast, then you can take a look at sample exercise 20.10 in your textbook for more practice. Let's try one more. Let's consider this reaction. So we've got silver ion is being reduced into solid silver. So when we buy silver salts like silver chloride for our school to use in reactions, it's very, very expensive because we can easily turn that into silver metal if we wanted to. So what I'd like you to do is calculate delta G sub F. So remember, that's the delta G of formation for the silver plus ion. And we're going to use the standard reduction potentials in this table, which I've shown for you here. And recall that the Gibbs free energy of formation of any element in its standard state is going to be 0. So, and oh, you might be wondering, why is this one also 0? And it's because we define this reaction as having a standard potential of 0. So if we remember this equation which we just learned, delta G equals negative NF E naught. If we define H2 and 2H plus as being interchangeable, they both have a standard potential of 0, then all of this turns into 0 for the delta G naught for H plus ion as well. So take a moment, calculate this on paper. If you'd like, you can check your answer in the back of the book with Appendix C. It should be consistent before you type it in. Good luck. And the correct answer for this one was positive 77 kilojoules per mole. So if you need more practice with this, take a look at sample exercise 20.10 in your textbook, or it might even be a good idea to read section 5 in your textbook under chapter 20. Good luck.